Hi ladies and gentlemen, in this video I tell you about the second experiment, that is familiarization of scientific computing. In this what we learn are the syntax for Python functions and simple Python functions. Then we will familiarize built-in functions. So let me start with that presentation. So the speech is organized into your learning outcomes, the syntax of a Python function, then a simple example of a simple Python function, then a function to compute pi and built-in functions, then a summary of your what you learned. So what you learn are you will learn the syntax of Python functions, then you will learn to write simple Python functions, then you will write a function to approximate pi. Then you will familiarize basic arithmetic functions such as absolute value, sign value, real, imaginary, complex, single function, etc. Syntax of a Python function is diff. It starts with the keyword diff, define, diff, then some function name, then arguments to that function, followed by a semicolon. Whatever is happening in the function, that comes as an indented block. I told you Python identifies code blocks by indentation. So statement 1, statement 2, etc. Then entered by a return. Return, it may return void or return some values. So note that keyword diff, then followed by the function name, arguments, followed by a followed by a colon. So after that colon, whatever comes after that colon, that is part of the function, and that is put as an indented block. The function ends with a return statement. So these functions should be imported in your main code. Somewhere you have a main.py, in that you can import this function, and you can utilize that function. Let us consider a very simple function, say the sum of two numbers. So you write diff sum sum x comma y, return x plus y. It runs the sum of x and y. You can write even in a command line. If I take a command line here, if I take a window here, I open a terminal here, I type, I'll make it a bit big. I type Python 3, and I can write from here, like right at the command line I can have it sum, say x comma y, followed by a colon. Now here you can see that it comes as an indented block, that return x plus y. You can see this. So if I write sum comma 15 comma 6, it runs, I'm sorry, it is 15 comma 6, so it is 21. Okay, 15 comma 6, it is 21. Or you can say 2 comma 3, 2 comma minus 1, it returns a 1. So this is how the functions work. This is how I write a function. This function can be imported to other Python modules, like I have a function here. I have this function here, sum x y, return x plus y. So I can run here, I can clear this, I can I should go to code. You can see these codes here. Here you have this sum.py. I can run here, run. Okay, now I can have another file in which this sum can be imported. Like I can have a new window. For here I can write from scipy import star, and here I can write from sum import star. Either I have to specify the path, or both should be in the same directory. Say I can say x equal to 23 and y equal to 48, 46. I can say print sum x comma y. So in this I can call as a main file. I can write as control as some main. I go to the same location. I go to courses, I go to CEC, wherever I am working on. Do ECL 201. I can go to talks and codes. Somewhere here I write a main.py. Okay, now this main.py imports my imports the function sum. Okay, when I run this sum function, it creates a Python bytecode, so that is available in the directory. So when I import the sum, it imports that bytecode, and bytecode this function returns that the sum of two values. So if I run main.py, you can see the value is returned at 69. Okay, the value is returned at 69, 23 plus 46. Now this is how I import this function, sum function. Sum is written here. Now import it into a main code in this manner. This is how I write a function. This is how I import a function into other codes. I told you that Python is a modular kind of language. Now let us compute another function, say a function to compute pi. Let us consider a function that returns an approximate value of pi based on this construction. So you can see that there's a inscribed circle. The diameter of the circle is 2 unit and the square is 2 unit. So the circle is unit circle. The unit circle of unit radius that is circumscribed by a square of side 2 units. So the probability that a point lies within the circle, so all the points inside the circle, they are marked blue. So what is the probability that a point lies inside the circle? That is area of the circle that divided by area of this rectangle. Okay, so you can compute probability by taking the ratios of area. So it is here it is area of the circle is pi into 1 square, because it is 2 unit pi r square, that divided by area of the rectangle is 4 units, so it is pi by 4. So that is number of points within the circle divided by number of points within the square, over the square. So pi is equal to 4p. Okay, so if I compute the probability and multiply by 4, that will be the approximate value of pi. So I write a function to compute pi. So here I write from scipy import star from pylab, some plotting modules are needed. So pylab import star diff some pi value n. So I define a grid, x and y grid, this as a -1 to 1 by n. N is some number, integer, so it is -1 to 1 with the increment of 1 by n. Here I put a n star star -1. This is a power of -1. It is 1 by n. It's a convenient way of writing 1 by n. Y is similarly -1 to 1 with the increment vector with increment 1 by n. So I some desired points I write as an array, blank array, and total number of points as another array, row or as another blank array. So for I in x and for I in j, what I do is to this row array I append the square root of I square plus j square. These are the points within the circle. So if this square root of I square plus j square is less than or equal to 1, if that falls within the unit circle, then you add those points to these desired points. So these desired points are actually points within the circle, and row array contains all points within the square. So if that magnitude is less, then what I do is I divide len, length of the desired points, that is the total number of points in desired points, that is the total number of points within the circle, that divided by total number of points within the the total number of points within the rectangle. So instead of doing a division, I did an inverse operation, that multiplied by 4, that returns my the value of pi. So return pi val, that returns my the approximation of pi. I'll go to this code. I will show you this code here. This is my pi val code. Okay, so this I can run on the command line, and if I apply a value for n, I can say that I can approximate it to pi. I can clear this. Okay, here I run pi val. Okay, if I say pi val 500, say 500 points, if 500 by 500, if I say, you can get an approximation for pi. You can say that is 3.1413, etc. Okay, if I say 750, you can have a better approximation. You can see that it's 3.1415 that way. The more the number of points, the better the approximation will be. So let me go back to my presentation. So some built-in functions are there in SciPy, etc. In the syllabus it is given the absolute value, real value, imaginary value, etc. complex value. They can easily be verified here. Like if I say x equal to some array 1, 2, or say complex 3, 4, okay, then 1j star 2, 3, okay, you can see that this is a vector containing 1, 2, or a list containing 1, 2, then 3 plus j4, this is a complex value 3 plus j4. My 1j into 2, that becomes a 2j, then 3 is a real value. If you say real of x, I say import numpy. I like to use numpy here, numpy as np, okay, and I can say np dot real. I use the numpy module here, real x. If I say, you can see that it is 1, 2, 3, the real part of that, 0, 1. If I say np.abs, this numpy is a very useful module, abs x. You can see that it is 1, 2, here it is absolute value of 3 plus 4, the 3 plus 4j, it is root of 9 plus 16, that is 5, then 2, 3. Okay, this is how I use the real value, absolute value, etc. Then what more are needed? Imaginary complex, okay, imaginary is there. Instead of imag x, np.imag, I will say np.imag x. You get the imaginary part of that. First two are real value, so its imaginary part is 0, then 4, then 2, then 0. Okay, this is how I compute these functions. Now when you compute sine, sinh, etc., you can I write another code for this. Here I import my SciPy and PyLab modules. X I write as a vector. Now I use arrays here. These are SciPy arrays. Okay, these are a real array of minus 10 to 10 with an increment 0.001. These values will be from minus 10 to 9. With sorry, minus 10 to 9.999. This vector will be from minus 10 to 9.999. 10 will be excluded. Okay. Unlike MATLAB, Python supports zero indexing. So y equal to sin x will give you the sinusoid of x. If I say figure 1, plot xy grid on, so this will create a first figure will plot my sinusoid, and if I say sinh x, it will plot the y equal to say sinh x. The sinh function is very useful in many communication purposes, computing and all. So plot x comma y1 will give me my sinh function, and grid is on, and show will show the plots. I can run it here. Where is that code? The code is here, sine sinh. Okay, sine sinh. I can run sine sinh. You can see that in the first figure a sinusoid is created. Okay, in the first sinusoid is created. You can see that in the second window a sinh function is created. Okay, sinh function is created. If I type x here, you can see that basis vector, that is minus 10 to 9.999. If I type y, you can see that's a sinusoid. y1 is my sinh function. Okay. y1 is my sinh function. What you learned in this session are, you learned the syntax of Python function, you learned to write simple Python functions, then you learned to write a Python function to approximate pi, then you familiarize a basic arithmetic functions such as sine, sin, abs, real, imaginary, complex, sinh, etc. using built-in modules. With this your second experiment is completed. So So thank you all.